Sorry, guys. I'll just redo the introduction. I'd just like to welcome all of you, and especially joining from those joining from YouTube. So the NSF colloquium has been there ever since TIFR, started having different faculties in different departments. So the natural sciences faculty sort of usually gets to meet once in a week at 4 o'clock. And this idea of bringing all the natural sciences faculty, physics, chemistry, biology, under one roof was started by Professor Homi Bhabha, the founding director. And it has been an age-old tradition for most of the people who have been in the TIFR system, the faculty members, students, PhD students, or postdocs, or even staff members. The NSF Wednesday colloquium has been very, very sort of engaging, as well as always provides a broad view of things. And the speakers, of course, Parthanil today, always bring in that broad view, so that even the members from different parts of natural sciences can connect. And today we have, interestingly, a mathematician coming in this forum. It's not very odd to bring in mathematician in the science forum, simply because, of course, they're doing all the hard work for us to sort of understand nature, they're bringing the language together. But sometimes it's difficult to sort of connect when we are actually working on a problem, whether it's physics-oriented or chemistry-oriented problem. It's sometimes difficult to connect, but you can appreciate the impact of it in our work in certain cases. So we have Parthanil today, who has been actually a visitor in TIFR for some time. He usually comes into the mass, visits the mass department quite often. I see him with Mahan, who is actually here today in this talk as well. So Parthanil actually comes from Indian Statistical Institute, Bangalore, and he works on probability theory with connections to the ergodic theory, operator algebra, geometric group theory, and hyperbolic dynamics. After completing his PhD from Cornell University and postdoctoral fellowship in Etihad, Parthanil was a tenure-track assistant professor at Michigan State University, where he first started as an independent faculty member. Before he came back to India and joined ISI, roughly into 2011. Almost 3 years or 4 years you spent there, right, in Michigan?
Yes, 3 years.
Yeah, 3 years. Then Parthanil has actually is of course won the Swarna Jayanti Fellowship, and he is young statistical scientist. He won the Young Statistical Scientist Award from the International Indian Statistical Association. But apart from that, I can tell you one interesting personal fact. Parthanil and I were in the same BSRP program in 1999, and we came to know each other during that time. There's some good memories of him and our birthday celebrations and other things. So without further ado, Parthanil, the floor is all yours.
Thank you, Mark. Thanks for the very kind introduction. I think it was all true, except one thing: I don't do hard work. Nor have I been to hard work. Very good. Okay, so this is a joint work with Ayan Bhattacharya, who was my PhD student. At that time, I was in ISI Kolkata, so he was a PhD student there. And Rajat Shubra Hajra, who was my colleague there, but both of them, Ayan is now a faculty member and assistant professor at IIT Bombay, and Rajat has moved to Netherlands, Leiden University. So before I start, I would like to thank Jyotish Man for inviting me. It's a great honor. And especially great because there are two issues. One is that, as you mentioned, I know many people here. Many of them I know from, say, 1999. So I know Jyotish Man from 1999. We are both BSRP students here. The things that I learned at that time, I'm still using in my research. So VSRP is actually pretty great. And also there was another one, VSRP, Anish Ghosh, who's my collaborator. So, and then I also know Tuhil, who's anyway, from my school days. So I know him even further back. Anyway, so it's great. And also right now I have collaborators here. So it's of course a natural thing for me to come here and give talk. So this talk is about branching random walks. But before I get into the business, because I see many scientists here, so I'm sort of nervous. So I want to start with an icebreaker. So it's more of an icebreaker for myself, so that I can. You don't see it, but I'm extremely nervous. I'm more nervous than Jyotishman, for example. Because that says it all. He was very nervous today. Okay. So first, I would like to say why this topic. I don't know. Is it possible?
Yes.
Thank you. So why this topic? So this topic has some connection to Indian railways. So I'll start with that story. So this was about a decade ago. I was traveling by train on a Sunday afternoon, lazy Sunday afternoon. And I met two school students who asked me what mathematicians do. It's a very good question to ask, but there was a context why they asked this question. So they, I think, were class 11 students, 11 or 12. They were very sincere. They were very sincerely studying whatever they were supposed to study, that they had something to read, so they were reading. So inspired by them, I thought, okay, I should also do some reading. So I had a paper with me, like paper meaning a paper that we were writing at that time. I was editing it. So my student had given me the 0-8 draft, I was editing it. So those were the days where I used to edit the hard copy, not on iPad. So I was editing, and then the students saw me. So one of them asked the question, so what are you doing? I said, okay, this is what I'm doing. And they were very excited. So they were like, oh, you're proving a new theorem. And I tried to tell them, no, it's not that new. It's like something was already there. I'm trying to improve it a bit, etc. But then one of them asked this question, the other one was rather silent, and then he suddenly said, so you're a mathematician. So I know what scientists do. What do mathematicians do? So this is the context. So then, of course, before answering him, I thought maybe I'll first ask him what he thinks of scientists. So I asked him, so what do scientists do? So I know there are many scientists here. Most of, my friends happen to be scientists, and many of them are theoreticians, and whoever are experimentalists are also not going to like the answer that the student gave. I'm being honest here, okay? So the student said, well, they just take a red solution and a blue solution and mix it and get a green solution out of it. So that was his answer. I said, well, okay, I was literally laughing, but I didn't express that. I said, okay, let me use this as an allegory and say that, okay, we do the same thing. We just, just like this, we just take a red theorem and mix it with a blue theorem, and hopefully we'll get a green theorem. There will be some surprise there. Don't be a violet theorem, it will be a green theorem. So that's what I answered him. So that's what I'm going to present today. And one reason why I'm presenting this particular work is that this was the paper, first draft, the 0-8 draft of the paper I was editing was about this one. Okay, the paper I'm presenting to. So there is some connection with those students, and I thought it's always good to connect with students using this paper, given that memory. Okay, so with that, let me start the business. But before that, let me just tell you, I know there are participants from online, and also there are people here. So I hope you can all hear me. That's one thing. If you cannot hear me, let me know, or at least let Jyotishman know in the chat. I'll try to go very, very slowly because it's a very broad audience. Please feel free to ask questions. And I would prefer, if you're here, of course, you have no other choice, but if you're online, please unmute yourself and ask if it's possible. If not, after each approximately 15 minutes, we'll take a break and allow questions and comments. Okay, it would be great if you ask all the time, but at this last time, please ask. In the end, also, we'll have a discussion session. So in particular, I want the talk personally to be interactive because I may not be able to express myself. Please ask questions. Okay, so this talk is about branching random walks, but let me start with random walk. So what is a random walk? So think of a completely crazy person walking on the road. And there are two crazy persons here. The person who's walking, there's another crazy person who has no other word, jobless crazy person. Sorry. Yeah. So what he or she did is he drew a number line on the street. Okay, so number will be only integers. So somebody has printed or drawn these numbers 0, -1, 1, -2, 2, etc. on the street, and this completely crazy person is starting from 0 in the street and tossing a coin, a fair coin. Suppose you have a coin which is fair in the sense head and tail both have 50% chance of appearing. So this person is tossing the coin. If head appears, he or she is moving a step forward. So taking a step towards plus side, +1 side. Okay. So first time, suppose the person gets a head. So moves to +1. Now at 1, there will be two choices again. Again, independently, the person will toss a coin, fair coin. If it's a head, he or she will move from 1 to 2, which is taking a +1 step. If it's a tail, he or she will move from 1 to 0, so taking a -1 step. Okay. So in this case, in this particular simulation, it so happens that that person got a head, so he went to 2. He or she went to 2. Okay. Then from 2, same thing. Either go to 3 or you go to 1, depending on head appears or tail appears, respectively. Okay. And remember that this coin is fair, so the chance of getting a head and chance of getting a tail are equal, and both are half. So therefore, with half probability, the person is moving always to the right, and with half probability, the person is moving to the left. Don't ask me why. It's a crazy person. Okay. So next time, perhaps it's a tail, so it's -1. Suppose again now it's a head. Sorry, so again +1. Okay. Then again it's a tail, so it's -1. So now moving to 1. Again tail. Okay, I'm just simulating 1. Again tail. This will go on. Tail again. So there can be multiple consecutive head or tails. Okay, even though these are important point is these are all fair coins and independent tosses. Okay, so I'll write it more mathematically later, but that's right now. So basically, what the person is doing is he or she is starting at 0, tossing a fair coin. Okay. If head appears, then taking a step +1, as I said. If tail appears, then taking a step -1. So either going right or going left, respectively. Now, once we take the first step, he or she takes the first step, toss a fair coin in an independent fashion. It's very important that the tosses are independent, which roughly means the outcome of the first toss should not have anything to do with the outcome of the second toss. Okay? So after the outcome comes, if it's a head, again take a step towards the right side, which is the +1 side, or you take a step towards negative side, which is -1. Now you have to repeat these steps 4 and 5 repeatedly as long as you want. This will constitute what is called a simple random walk on integers. Why on integers? Because you are always, at any point, we are always taking an integer step, 1 plus or -1 step. Therefore, since we are starting at 0, we are always going to be on some integer. It can be a negative integer, it can be at 0, it can be positive integer, but this is always on integer. So that's why this is a random walk on integers. Simple refers to the fact that every time the step size is either 1, okay, step size is 1, either on the plus side or on the minus side. Okay, so and they are happening with equal probability. That's why it's called simple random walk. Okay. Any question, comment on the model? This was simple so far, so I guess it's okay so far. Have I lost anybody yet? Okay, so far so good. So let's move on. Okay, so I'll just quickly do the movie again, just to see if I run it fast, how it looks. So, go back. Yeah. Yeah, this is how the movie looks when you see it. Okay. Okay, so now, instead of simple random walk, I could have actually started with what is called any random walk, but I didn't want to do that because I wanted to start with a simple example. So what would be any random walk? So instead of taking up, roughly speaking, what it means is this red thing that I've written here. Can you move that cursor? Is it possible to move it away somehow? It's coming from there. Sorry. You just move it up there. Oh, yeah, that's it. Thank you. So any random walk means the dynamics is going to be the same. So the person will start from 0, but instead of taking +-1 steps, Now the person can take any step, will allow any integers, potential. How am I going to make it formal? So what I'm going to do is for every integer I, remember integer means it can be a strictly positive integer or a strictly negative integer or zero. So integer means all integers, okay? For every integer I, I'll fix a non-negative number pi, okay? For every I, you have a pi in such a way that the sum of all the pi's is equal to 1. Okay, so this pi will basically give me the probability of moving from 0 to I. If you add all of them over integers, that should give you 1. So what you do is this, you start at 0. Now it will be clear the dynamics. Take a step I with probability pi. Remember, pi is sum up to 1. So therefore, you will definitely take an integer step. Okay. Now I'm not saying that all integers have positive probability. You may have many integers for which it will be 0. That's allowed. Okay. They're all non-negative numbers. They just add up to 1. That's all. Okay, if you know what it is, it's a probability distribution on the set of all integers. If you don't know it, don't worry about such terms. This is good enough. You take a step I with probability pi in an independent fashion. Remember, once you go take the first step, you have to again toss the coin independently. Now you're not tossing a coin. You're just moving the step according to this probability distribution, whatever that means. So what you do is in an independent fashion, you take another step j. Okay, now since you're taking a step j, you will do it with probability pj. Pj doesn't mean poor joke, it means step size. So the probability of taking a step j. So this was a poor joke. Anyway, so I repeat this step 3 again and again. So this gives you any random walk. Now, if this looks too abstract to you, I'll give you some examples. First example is when you have simple random walk. We basically what we do, we take the steps +1 with probability half, -1 with probability half, all other probabilities are 0. So therefore, what I have is I have probability of P of 1 is half, P of -1 is half, and P of other i's are 0. So let me take 2 more examples. So another example is when say P1 is 0.75, I'll draw a figure here. So 0.75, so you basically go from, sorry. So you go from 0 to 1 with probability 3/4, which is 7.75. And then you go from here to here with probability 1/4. So 1/4 of the time you're going to the negative side. 3/4 of the time you're going to the positive side. In this case, P1 is 0.75 by 3/4, P -1 is 0.25, all other PI's are 0. Now this is called nearest neighbor random walk because you're going to your nearest neighbor. So if you're here, you're either going here or here. Either left or right you're going, but there's a bias here. There's a bias towards the positive side. Okay, so there's a bias towards the positive side, so it's called a biased nearest neighbor random walk. In other words, if I had an unbiased nearest neighbor random walk, which means if I had 0.5, 0.5 both sides, I would just get back the simple random walk. Okay, so this is not simple because there is a bias towards the positive side, and it's if you think about it for a minute. Obviously, if you start from 0, since there is a bias towards the right side, you go on, you will come back from time to time from this side, but most of the time you'll go on the right side, so you'll move off to infinity to the right. That's kind of expected. These things can be proved, but this is kind of expected. Anyway, it's not so important for my talk. I just wanted to give you some intuition. Similarly, here is a nearest neighbor walk with some laziness. So this guy, this crazy guy is also lazy. Okay, so what he or she does is, okay, you can go from 0 to 1 with 70% chance, can go from 0 to -1 with 20% chance, but there is a 10% chance that this person will actually, sorry, this should be 0.1. This person will actually not move at all, just stay put. So this is called lazy nearest neighbor random. Okay, in this case, it's a lazy and biased nearest neighbor random walk because you still have the bias towards the right side. But this lazy random walk is an example where you can stay put as well. So you don't have to move all the time. Such random walks are actually play a very important role because they satisfy something called aperiodicity, which helps, etc. But let's not go into those details. But the point is, these are just examples. So with the examples, is the notation clear? So you go from anywhere to anywhere, pretty much you can go, but you will follow a particular pattern. And this pattern doesn't change with time. That's the most important thing. At any point, Remember last time at any point in simple random walk, I was tossing always a fair coin. And I was tossing this independently. Here also, I'm going to toss, well, I'm not going to toss, I'm going to use this probability distribution to take a step. I'll use the same damn probability distribution all the time. And I'm going to do it independently at each step. These are the two crucial things to observe. Is that clear? Is there any question on the model? Because if you don't understand this, there is no way we'll understand what is a branching dynamic. Yes, please.
I have a question that how this positive bias is built up.
Oh, okay. How do you simulate such a thing? Is that what you mean? No, that's a very good question. Okay. So there are many ways to do it. If you have a coin which is 75% time giving you a head and 25% time giving you a tail, then it's okay, easy. But suppose you have a fair coin. Here is one way you can do it. Suppose you have a fair coin, you toss it 2 times. If you get it both head or tail, okay, or maybe both heads, tail head or head tail, you move towards the right side. That has probability 3/4. If you get tails both cases, then you move towards the left side. So every step you are doing 2 tosses instead of 1 toss of a fair coin. Okay. Is that clear? How you do that?
But still it is independent, right? How it is.
One time is okay. Next time you do another coin toss independently. 2 times.
But what is the chance that you do that side? Maybe it will come back.
No. The thing is that 3/4 of the time, this is just an intuition. 3/4 of the time you will move to that side, 1/4 of the time it will come back.
Similarly, you can do the negative side.
Exactly, you can similarly make it. So what will happen is if you go on running it, you will see that there is a drift towards the right side. It's not that you will see it immediately. It will take time. But eventually it will go on moving. There is a speed towards the right side. Right? This is the right language. There is a speed towards the right side. Okay, is that clear now? Okay, thank you for the question. It's always good to ask questions, and also for a speaker, it's great. That means that you are trying to follow. Okay. Yes, please.
In these random walks, when you are drawing from the distribution,
Yes.
should we keep the distribution always same for?
Yes, that's again, I wanted to stress that as a very good question. Every time the step size distribution, how much will I will go from wherever I am will be fixed. So in other words, if I'm at 1000 with probability pi, same distribution pi, same number pi I use, I'll go to 1000 plus I. Okay. So every time I'm using the same distribution, it determines the step size. That's how long the step should be. Okay. Step size distribution is always the same, and they're all independent. It's very good. Thank you. Anything else? Okay. So now let me give you a little bit on. So there is this talk by Mustanzi Verma, who used to be a faculty member here. So in the DTP.
The director.
Exactly, he was also a director. So he gave a copy with Curiosity talk, where actually I couldn't be there because I had some work, but I did attend it online. So at that time also, I didn't attend it online. What I did is later saw it online. Yeah, I don't know whether it was live or not, but at that time, so if you look at it, it has like 1,265 views. So it's quite high. This is pre-COVID time, remember. Pre-COVID time, not many people would go online and check things out. This is a new phenomenon, right? So at that time, so many views. So this is basically what he talked on, what Mustanzi talked on is random walks in science, essentially. And what he said, I want to highlight this part. By the way, this link, you can very easily search the Random Walks in Science by Mustanzi Verma, copy with you. But this is a series called Copy with Curiosity, which is organized in ICPS, copying something from TIFR. What is the name? Okay. So it's so anyway, this is what he said is random walk has become an enduring paradigm across the sciences and mathematics. In particular, I can tell you statistical physicists use this a lot because particles tend to move in a random walk fashion. And then also something completely unrelated with physics apparently also uses random walk that I know of, that is financial mathematics. Okay. So that uses random walks. Also insurance mathematics. So financial econometrics especially uses random walk, and also insurance mathematics also uses. So their random walks come very naturally. claim sizes, etc., etc. But the point is that these are all used, and their questions on random walks become very important. So this is a very important concept in science, not just in mathematics, and there is a lot of literature on it. However, I'm not going to talk on random walks. My talk is on branching random. Now, what is a branching simple random? Before I give you a formal description, let me first show you just the movie, just to tell you what will happen. You will see that now the particle sizes are going to increase. Earlier, there was only one particle, only one random walker, so to say. Now, number of random walkers will keep on increasing in some way. And I'll tell you the dynamics later. Let me first show you the movie. So, I want to do it again. So, this was time 1, time 2, time 3, time 4. You see that first time there were 2 particles, sorry, 0th time, this is time 0. Okay? There's 0, at origin there is 1 particle, then there are 2 particles, there are 4, and there are 8. Okay? Not hard to guess, the next step will be 16. So what's happening exactly? So this is called branching simple random walk. So you start with 1 particle at time 0. So instead of thinking of a crazy person, let's call it a crazy particle, okay? Because that's easier now to explain, because now things will split, etc. This crazy particle is special.
So the number of springs and number of particles is fixed into that's not is that deterministic?
I'm starting with a very simple model. So so Mahan is right. I mean, he always catches me off guard. So always whenever I'm doing that. So he basically what he says, I'm concentrating on, I should call it binary branching simple random walk, or branching binary simple random walk. Because I want to start with the simplest possible model and I address that question later. Yeah, thanks. Thank you. Any other question? Okay, so let's assume this very simple model where, so what happens is the following. In generation 0 or time 0, but the word time and generation I'm going to use in an interchangeable fashion. Okay, so at time 0, so time here is discrete. You can call it an epoch if you want. Okay, just let's call it generation. At generation 0, you have only 1 crazy particle at origin. Okay? Suppose everything is happening on the number line just before. So integer line. Just like before, the random walks. Only difference is, now this particle splits into 2 particles, and each of the new particles move somewhere. Let's say each particle is moving like a random walk. Each particle has its own coin, and these 2 coins are independent. Each particle, each new crazy particle is tossing a coin. If it's a head, that particular particle will move towards +1 side. If it's a tail, that particle will move towards a -1 side. The other particle is doing the same independently of the first particle. Okay, so that's what is happening here. In this picture, you see that the first particle is splitting. This splitting is also called branching. Okay, it's like a branch of a tree, right? The way the picture looks. That's why it's also called branching. So this branch
is independent random walkers.
Exactly. So basically what we are doing.
Order distribution.
Yes. So basically what we are doing, so what Pratishman said is correct. You have 2 particles, both of them are doing random walk, 1 step of the random so far, right? Either +1 or -1 with probability half and half the step. Independent of each other. Very important. Independent of each other. Oh, so you're either going to +1 or going to -1. So in this case, say one of the particles went to +1 and other one went to -1. There is no guarantee that this will happen. Both of them can go to the both same one also. But in this case, it so happened that they went to different ones. Okay. Now, next step. Each of these particles are again splitting into 2 particles, or branching into 2 particles. Each of them again. So that means there are 4 particles in total. 4 crazy particles now have 4 independent coins, 4 independent fair coins. Okay, all of them are tossing the coins. Whoever gets a head moves towards +1. Whoever gets a tail moves towards -1. Okay, so here, for example, this particular one, maybe this the one that was at 1. Okay, +1. Okay, that's basically what happened. It split into 2 parts. And then both of them got head. So they both move to class 2. Similarly, the one at -1, again, split into 2, both of them tossed, but one of them got head, another one got tail. So one moved to 0, one moved to -2. Similarly, this, by the way, this formed generation 2, sorry. I started with generation 0, where one particle was there, it was at origin, then generation 1, then generation 2. Generation 3 would be there will be 8 particles because, as Mohan observed, I'm just splitting it in a binary fashion. So we are splitting each particle. So we have the particle at -2 is splitting and going, say, one of them got into 2 and one of them got a head, another one got tail. Similarly, other things are happening. So I can just explain. You can see what's going on from the picture. Each of them is splitting into 2, and then there are total 8 particles. All of these 8 crazy particles have 8 independent pair points. They're tossing it, and depending on the outcome, they're just moving it. So as Jyotishman correctly observed, if you follow a particle and its genealogy, or rather, if you go down the path, like for example here, if you look at one particle and then its offspring and offspring of that particle, and you follow one line of genealogy, it's basically a random walk. Because, say for example, let me color it easier. Say for example, let me color it differently. So say I follow this path like this. So from here I come here, then I come here, then I go here. Okay. So if you look at this particle, so I'm basically finally coming at this particle and follow its ancestors fully. Basically, what has happened is a random walk. Because each step was an independent, by the way, everything is happening independently. All the new particle steps are also independent of the previous generation, etc. I should have mentioned that too. Everything is happening independently of this. Everything is independent. So therefore, I'm just getting a random walk along each path. Every time there is a branching, which is splitting, and there is so many random walks together, coupled together. That's why it's called branching. And in this case, it's a binary branching random walk because there is splitting into 2. I'll first describe that and then address Mohan's question. And then it's also simple because it's always taking a +1 and -1 step with equal probability, just like the random walks. Okay. Okay. So before I describe, sorry, yeah.
What do you care about subdynamics?
Yes, I'll come back. That's a very good question. Yeah.
I'm going to put a probability distribution there.
We will do that. We'll do many things. I'll come back to that. That's a very valid question. I have answers to those. Yeah. Okay. So far, I'm doing good. Every question anyone asks in the room, I have answers to that in some slide or the other. Okay, sorry. So before we move further, let me first ask, is there any question on the dynamics? I'll again explain it. I'll write it in words. You can ask me at that time as well. Okay. So here is again the video. I'll go over it quickly. So maybe good time to give a pause. So do you want to ask anything now or want to wait for the more wordy description of the same thing and then ask? Please go
I
ahead.
have a question to dynamics. Like,
Yes, please. Yes.
how the
Yes.
will always can you move one particle to -2 and other to 1? Like why branching from 0 to
So say you are at -2 or no.
so like in generation 0 we are 0.
Yes.
Generation 1 particle goes to -2, other goes to 1. Can this
Yeah, you can do that, but at this point, no, because I'm using the word simple here. Since I'm using the word simple, you always take every new particle will take either a +1 or a -1 step at this point. Later on, I'll remove this restriction.
+1 and -1 or maybe both in the same minus.
Both can be, yeah. For example, here,
Yeah.
this one, yeah. Both of them took plus. Yes, they are.
If I look at generation 3,
Yeah.
I have 8 random walks.
Right.
If I run one movie backwards, there will be 8 random walks
Yes.
which seem independent. But they
Yes.
seem to know something about each other, right?
Right.
They meet in pairs.
Right. The very good point what Kedar said is that there are 8 random walks, but what makes this analysis really challenging is that these random walks are heavily dependent. For example, if you look at this particle and this particle, they are both coming from some random walk. I can color them also, but the point is they have a common parent, and therefore the random walk are heavily dependent. 2 paths are common. So there is heavy dependence there. So these are 8 random walks at generation 3, but these 8 random walks are heavily dependent, which makes the analysis very, very challenging. Okay. Also, there is something called stationarity. There is no stationarity also, because you cannot just shift and get the same distribution. So all the nice things that we know in statistics or whatever, physics, all of these things are not there. So that makes it challenging. Yeah. Very good. Thank you. Anyone else? Yes.
So now I have done it for 3 steps. So if I do it for any number of steps, for a large number, at then should I expect that the center of gravity is center at 0 or
No. Well, it depends on the distribution. If the distribution is symmetric, then yes, you'll expect it to be close to 0. That's a very good question. If it's not, then you will see a drift there also. Yes. Actually, the whole talk is about what happens in the long run. So you're very, very ahead of it, slide in terms of slides. Okay. Anything else quickly? Yes, please.
So I have a question on the application.
Yes.
So let's say that we have a distribution, probabilities, and right? I want to sample from the distribution.
Yes.
Some, like you get MCMC or something.
Right.
But now I'm going to apply what this thing. So will I be ending up in having more particles in the place where there is more probabilities?
Well, I think what you said is correct. So in the sense that if you sample and do it like this, you will see that. But that may not, I mean, you have to like every step, you see that it's exponentially growing, right? So you have to simulate too many random variables. So, but there are ways, I think, but we haven't done it. I have a feeling there are ways to sample them in a more efficient fashion. So I exactly understanding what you're saying, understanding the final distribution and trying to sample using some important sampling. Yeah, there are ways, I'm sure, but we haven't done the work on it.
Is it about what you say it's not stationary?
Right.
So what's the body level?
How to simulate it. So yeah, basically one way to simulate it, you simulate, so up to say generation 3, how many step sizes were there? You simulate all of them. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so there are 4 here, so 8 here, 8 plus 4, 12, 14, right? So all 14 steps plus minus 1 steps you generate and then you do it. That's one way, but this is heavily costly with algorithms. So, but I'm sure there are better algorithms which somebody needs to look at using some kind of important sampling. Yeah, that's a good question. Thank you. Okay, so let me move forward and now I'll verbally describe this branching simple random walk on integers. So you start with one particle that was position 0. This is the 0th generation of generation 0. Okay. Now what you do is the particle branches. So instead of splits, I'll use branches. It branches into 2 particles. Each new particle tosses its own fair point independent of each other and takes a step plus minus 1 depending on whether head or tail. Okay. This gives rise to the first generation. We have already seen this in the picture. The picture I think was much better than these words. Each particle repeats these steps 2 and 3 independently of each other. So every time, not only independent of each other, actually I should have mentioned this more clearly, it's also independent of whatever happened before that. So every damn thing is independent in that sense. Okay? Every step is independent. Plus minus 1 step is independent. Okay? So this is just going on and on. You'll get this branching random. So this is a verbal description, but you have to see from the picture at this. Is there any question on this description? Now the time has come where we'll move on from simple branching random walk to not necessarily simple branching random. So that's just like we did in the random walk case, which will address one of the issues that I think one of you mentioned. Another will also allow not necessarily splitting into 2 particles, which will address Mohan's question, although he's not around. Let's move to another talk. So, yeah, so what is any branching random walk on integers? Yes, please, go ahead.
So if
You don't have to call me sir, just Parthanil is enough. Yeah.
if I do a random walk and record it and then play it in reverse, so would it still be a random walk?
Random walk in reverse, it depends on, yeah, it will be a random walk. It may not be the same random walk. For symmetric case, yes.
For simple.
Yeah. But branching random walk won't be a branching random. Random walk, yes. something, some other
So
distribution.
it seems to me that it is not random in a sense that, so it is the question that Kedar has got me thinking. So when the branching happens and then everything distributes, if I can still say that the opposite is the random walk, then if I play that movie, then everything will converge to zero.
Right, it will. That said, in that sense, yes. But that's not more interesting. More interesting is the forward direction. Think of your bacteria. So instead of particle, everywhere I have said particles, it can be replaced by a bacteria. And you can think of them, the bacteria are moving on a line or something. Everywhere, it's more interesting when the process goes on for a long time, what happens.
What I wanted to ask was the question about the definition of it.
Okay.
In a more abstract sense.
Right.
It seems to, so the backward movie also seems to satisfy all the definitions of
Yes,
that it takes us
Definitely.
everything.
Yes.
But it doesn't seem random because everything is converted.
No, but that's because I started at zero. If I started at a random point, then that won't be the case. I started at zero, that's a special case. I just wanted to make life simple. If you start at a random point according to some distribution, then that won't be. That's a good question. Okay. So same dynamics, like splitting and then branching and then, splitting or branching and then each particle doing its own random walk, except that now the state sizes of each new crazy particle is not necessarily going to be plus minus one. Okay. So you can take any integer step, which means the same thing. For every integer I, you fix a non-negative number of pi in such a way that the sum of all these pi is equal to 1, just like in the random walks. We have seen many examples there. I'm not going to give more examples here. Now, what you do is you start with one particle at position 0, which gives you the 0th generation. Then the particle branches or splits into two particles. Each new particle takes a step I with probability pi independently of each other. Just like before, every particle is doing this random, more general random walk now, but now independently of each other. Now, this gives rise to the first generation. This is generation 1.
And still you have the fixed probability distribution for each generation.
Exactly. So for each particle, so that's again, I wanted to stress it, but good that you've already stressed it. Each new crazy particle follows the same probability distribution to take a step. Okay? Just like random walk.
Sure.
The theorem is very similar, except that every time the number of random walker particles is increasing, it's doubling, so making it more complex, that's all. Okay? So this gives rise to each particle will now repeat steps 2 and 3, and this process will go on. And everything will happen independently of each other, and also whatever has happened in the past. Okay, so for branching simple random walk, of course, we'll take the probability distribution that gives P1 equal to half and P minus 1 equal to half and all other Pi's. That's just like that. Now, this addresses one of the questions that one of you asked. I think, can you do other kind of steps? Yes, that's the question. Now, instead of that, now I'll make it a little bit more complicated, and I'm not going to completely make it rigorous. So far, everything was happening on integers. I'm going to make it on real line, but I'm not going to make it more rigorous than this. I'll just put everything under the carpet. Okay? So what I will say is that everything is same, except that step sizes does not have to be an integer. It's a completely crazy particle. Why will it only take integer steps? So now you have a crazy particles, but you don't have that crazy person who marked this 0, 1, 2, 3, etc. on the road. So the road is free. You can take any kind of step. The particles can jump anywhere according to some probability distribution, which can be made rigorous, etc. Don't worry about it. So you have already got the idea when the step sizes are integers. Instead of integers, you can have now the step can also be square root of 2, for example. Why would someone do that? Nobody knows, but assume that it's a crazy particle, so it can do it. Remember, as I always feel, in many cases, even though life is discrete, continuous is a good approximation to that sometimes. So that's a philosophy you can always keep in mind. Okay, maybe everything is happening in a discrete fashion, but we are making this continuous thing helps to approximate. Okay, so if you have ever seen it, a binomial distribution, have you ever heard of it? That can be approximated using normal distribution. The philosophy is that binomial is too difficult to compute, but normal curve everybody knows. So we use normal to approximate binomial. So that's the philosophy you can always think of. Anyway, this part answers very lightly Mahan's question. Good that he's not here. So otherwise he would kill me because I have put it in a lighter shade. So the number of offspring particles can also be any non-negative integer. In the sense that I don't have to have two particles. It can happen that every time I am having splitting into three particles. So at the third step, instead of 8 particles, I'll have how many particles then? 27 particles. Okay. So this can go on. So instead of a fixed number, I can also make that random. Okay. Yes.
So is it a random number, but is it same for all the splittings, or can it be?
It can be different. So it will be again this random number. That's why I'm not making it fully rigorous. The random can be different, but the point is it's the same. All of them are random, but they're following the same distributions. In that sense, they're same. So number of splitting also will follow a distribution on the non-negative integers.
Can it be zero?
It can be zero. I said non-negative integers. Very good point. There are some points which will just die off. So their deaths are allowed, unfortunately. Okay. So deaths of particles are allowed. So think of them as bacterium, a colony of bacteria. Start with one bacterium, splits into a random number of bacteria. All of them move in the line. So it's a bacterial colony which is living on a very thin strip net. Okay, and they're moving. Each of them producing a random number of bacteria. Some of them dying off and moving. Okay, so if too many of them die off and it's a bad bacteria, then we should be happy. If it's a good bacteria, then we won't be happy, etc., etc. So we need to know how they behave in the long run. So that already is there. Okay? So that question somebody already asked is important. But I'm not going to make it more rigorous than that. I'll just say that I'm making 2 amendments. One is that I'm allowing not necessarily integer steps, but in whatever way I can. And I'm also allowing instead of 2 particles all the time, that's boring. I'm allowing instead of also it can have 3 children, more than 3 children, whatever, 0 children. All of these are allowed in some way or the other. And the important point is all of these distributions should be independent of each other. Okay? Everything. Okay, fine. This model was actually introduced by Begins in 1976, exactly 2 years before my birth. But then there are also others like Hammersley and Kingman who laid the foundations of this work. So therefore, whenever people give a talk on this topic, they always mention Hammersley, Kingman, and Begins as at least in the probability literature, these are the first ones. I mean, maybe in statistical physics they appeared even earlier. I don't know. I'm not so familiar with the statistics literature, but yeah. Okay, sorry, statistical physics literature. So, any question? This particular slide I know is very vague, but I deliberately kept it vague. I don't want to make it any more rigorous. Okay. Any question? Yes.
So, in a given generation, where all the particles will split the same number?
Not necessarily. It will follow a distribution according to a probability distribution. See, it's like this. So, for example, when you're taking a random walk step, each particle, not all of them are moving towards +1, right?
No, that's not right. Suppose you have the generation 2.
Yes. Suppose you have 4 particles in generation 2.
4 particles.
Yeah.
Then each particle, so one particle can split into 3, another particle can split into 5 and so on.
Yes, it's allowed. It's allowed. All of them independently of each other will choose from this distribution. It's called progeny distribution. Okay. All of them will choose from a particular distribution that will determine who will have how many children. There's a distribution. So yeah, what you said is correct. One can have 3 particles, one can die off, another one can have 100 particles, etc. Can all are possible. Depends on the progeny distribution. How many you will see at what?
So die off is represented as what?
At 0. So 0 particles. So it will. Yes, it's just after. So this picture will move. It's in the tree. It's like a tree, right? If you go back to, let's go back to this picture. In the tree, it will become a leaf. Yeah. In this tree, it will become a leaf. So you don't have any children. Okay. Yeah. Okay. So let's move on now. So, why is it important? This question Tuhin asked, and that's a valid question. I think somebody else also asked, and that's, I think, question I need to address. So, it is important because of many reasons. They appear in many contexts, starting from mathematical biology to statistical physics. Well, I give some story like particle or bacteria, so that's a sort of to convince you. But the point is, it can be used to describe how a growing population of, say, as I said, bacteria or particles invades a new environment. Of course, in this case, I'm having the environment is just a line, but more generally, so here it's a very simplified model. This is, I think the physicists use this phrase called toy model. Right? We start always with the toy model. And the idea of toy model means that it's a model where you can easily understand things. And then you get an intuition and use your intuition there, then go to the more complicated models. And maybe you cannot fully solve it, but you can at least try to get some idea, some hunch, etc. Okay. So this is a toy model where we are keeping everything simple, only allowing particles to move in a line. One thing that I should mention is that particles are moving. Don't think of that they're moving on a line. Think of it they're moving on a very thin strip in the sense that they're not colliding with each other. Some of them are avoiding each other. There are even more complicated models where colliding is allowed. And after colliding, they can just, go back using, conservation of momentum, etc. That's allowed. Or sometimes they collide and kill each other, explode or whatever. Or sometimes they can collide and become one particle and move in one direction. So there are various things that are possible. But we are making life very simple. We are not allowing any of these. We're nice people. We don't want to kill each other. Okay? So the particles are nice people. They don't want to kill each other.
One question. So apart from the dynamics, the way you are thinking out, and you say the physics is in the probability distribution itself.
Yes.
Can you make a statement which doesn't depend on particular probability distribution?
I'll make some statements, some qualitative statements I'll make. They can be made more quantitative. Yes. Yes, that is the goal. So that is in exactly. So if the answer, that's a very good question. So if the eventuality of this system depends on the very distributions that we choose, then what's the point? Every time you have to do a new calculation. That's not good. So we should look for some kind of universality. Okay, there should be some universality class, and you should try to converge to them. So in some sense, you should have some universality in this world. That's a very good question. I'll answer that. This talk is about that only, in some sense. Okay. So here we are allowing only to move on real line, or at least even on integers. Okay, that's also allowed here. Okay. In a more complicated model, we can allow particles to move on this table, on this surface of this table. That would be a two-dimensional model. Okay. Or in a box in this whole room, that is a three-dimensional model. Now it can so happen that, say, you start in this room some branching random walk of some kind of particles. If the density becomes too high in a corner, it will explode. And just say this is just trying to give you a story. So therefore, what happens to these particles, how the density changes in various areas, does have some impact on the physics of it or the biology of it. Okay? If it's a bacteria, too many bacteria in one part of your body may actually harm your body. So therefore, what happens in the long run, how the particle configuration or the bacteria configuration looks like in the long run is a very, very, very important question. So what we are going to look at is the following. So the purpose of this talk is we'll restrict ourselves first of all to this very simple model where things are moving only on the line. Even you can think moving on integers if you like. We'll look at what is called the long run configurations of the positions of these particles. Now what do I mean by that? Let me be a little bit more specific. So recall that a branching random walk, if you don't know anything, this is the take-home message. It's a growing collection of particles or organisms that start from a single particle at origin, and then they branch and spread or split and spread independently of their positions and other particles. And this is the summary of all the slides that I have given so far in some sense. Okay, it's a one-sentence summary. Now, if you let this dynamics, as somebody already asked, run for a very, very, very long time, say million generations. Okay, so in case of bacteria, they'll split very fast and they'll quickly arrive at million generations. So the epoch may be like 1 nanosecond or something, 1 femtosecond or whatever. And then somebody has a nice camera where that person takes a picture of these particles on this line. How would this picture, this snapshot? You can think of this dynamics as a video, and then you stop the video suddenly. You see a snapshot. How does it look like? It's a very vague question, but this is what I'm trying to answer. So, in other words, this is I'm looking at what is called the long run configuration of the particles. Am I doing okay with that?
Yes.
So the long run part, don't be scared by just 115. I'm not going. There are a lot of white pages in here. In case anyone is scared, don't do that. Okay, so I'll go up to maybe only 114.
We know the problem is to talk.
Okay, so the long-run configuration, as you can expect, is very important in statistical physics and biology, and also in probability because we can write papers in our journals. Right? That's very important for us. So that's why we're interested. Sorry. Yeah.
So how do we define the long configuration? And this is not, I mean, this is not going to have steady state, right?
Yes. So okay. So I'm going to be a little bit more precise later, but roughly it is basically after a long time you see all these particles. How do they look like the entire system? But basically what it means is the following. So you fixed two numbers, and after error generation, you see how many particles are there, or what fraction of particles are there in between those two numbers, things like that. But the point is the numbers, you see the whole system would be growing in some sense, right? So numbers have to be scaled properly. There is some scaling involved. I'm being very vague. Okay. But then after some scaling, you have to look at those particles. So in other words, another way of thinking of it, this snapshot is not taken using my eyes. It's taken under some microscope. Okay? I'm looking at some particle and near some neighborhood, so I'm magnifying it or something, and then I'm looking from something like that. Think of it. Okay, so I'm going to keep it very vague, but if you want, we can discuss it. Okay, so now I'm coming to the title. By the way, this title, Two Conjectures and a Theorem. It's inspired by a movie. Can anyone tell me which movie it is? There was a part, right? My title was Two Conjectures and a Theorem. And the theorem, the T, alliterates with two. Does it give you a hint? Come on, you guys are supposed to be movie buffs. There's some movie showing. Every time in VSRP, I was always looking forward to the movies. It's a British comedy movie. Is that a good hint? Generation gap, man.
You're really your age.
I know. So if you haven't seen it, I think it's a wonderful movie. You should watch it. It's called Four Weddings and a Funeral. So my postdoc advisor is very good at coming up with good names. And they wrote a paper called Four Theorems and a Financial Crisis. And that's, I think, it's a very good paper to read. I mean, if you don't know anything about financial crisis, you see they'll follow something. So he writes very good. So my title is sort of inspired by him. So every time I make such a title, catchy title, I send it to him. And he says, yeah, good, you're following my students. Anyway, he's a retired person now, but he's Belgian. So he's Belgian Flemish. So he's extremely, he has a very good sense of humor. Okay, so what are the two conjectures? So this is where the two statistical physicists come in, Bernard Derrida and Eric Brunet. Eric Brunet was Derrida's PhD student or postdoc, something, PhD student. Right? Yeah. So they're both in ENS, École Normale Supérieure, Paris. So they had two conjectures on the long run configuration of the particles. As the time goes on, my talk is going to become bigger and bigger when you throw terms without explaining them. So what they said is that in this 2011 paper, which came out in Journal of Statistical Physics, they said that the long run configuration of particles is a decorated Poisson point process. By the way, how to pronounce Poisson? P-U-O, think of it as Poisson. That's apparently correct. My French collaborators tell me. Anyway, so I have some French names here, which I'm not going to pronounce correctly, because they cannot pronounce my name. I'm not going to. Yeah, anyway, this is going to be recorded. Sorry. So this is a decorated Poisson point process. And this long run configuration of particles is supposed to exhibit some kind of symmetry problem. We know if you have any idea about limits, etc., everything, any limit satisfies certain symmetry. In physics, you see these kind of things, etc. And that symmetry is sort of somehow inbuilt in the system in some way or the other, which sort of get manifested in the limit. Okay, so here something like that happens. And I'm going to promise you, I have shown two terms at you. First one is too hard to explain. Second one, I'll give you some idea what it means. Very vague. As I said, as the time goes on, things will become bigger and bigger. Okay, so the question that Brunei and Derrida asked in the same paper was that are 1 and 2 the same? In other words, being a decorated person-point process is it equivalent to exhibiting superposibility problem? Okay, so are these two the same thing? So this was answered by a French guy whose name I'm not going to pronounce correctly, as promised. So this was proved by Pascal Maillat. Who would pronounce it as Maillat? Come on, Maillat. Okay, so Pascal proved, I'll just avoid pronouncing the last name. Pascal Maillat proved in 2013 that they are actually. And unfortunately, or rather whatever, he had to assume some conditions on the distribution of the movement. Okay, every time you're moving using some distribution, remember? If it's on integers, there was every I will give you some pi, remember? So that step size distribution, how much you will take a step at a point, that distribution will play a key role. If you assume certain distribution, then, okay. So it's not about the distributions, but yeah. So this is about answering the question. So sorry, I'm sorry. So under certain conditions, he could prove that these two things are equivalent. The conditions are, I'm going to keep it very vague. Now, these conditions can be interpreted as on the system or all the distributions. Under that assumption, Thomas Madhu, I think this is I'm pronouncing correctly, proved that in 2017 that actually Brunei and Derrida conjectures 1 and 2, which are now equivalent, thanks to Pascal Maillat, that these two are equivalent. It's enough to prove one of them. Actually, I think he proved the second one. He proved that it exhibits what is called superposibility property, and hence, thanks to Maillat's theorem, it's a decorative force on campus. So there was some condition, yes.
What is the meaning of superposibility?
I'll tell you. That's again, I'm answering another question that is there in the slides. Okay, so the key question is what is the conditions in norm sense? But before I ask that question, I should at least tell you what are the conditions. I'll do that. Before that, let me answer this question. Okay, what do I mean by superposibility? What is superposing, by the way? Superposing means putting two pictures together. Right? By the way, many times we use the word superimpose. That's wrong. A British person told this, I believe. British. Yeah. So therefore, you should use superpose. Anyway, so what is superposition? Suppose you have this picture, rectangle which is red. Well, the border is red. And you have this picture, which is a union of a blue hexagon and a green star. Okay. If you superpose these two pictures, this is what you're going to do. So in other words, what I'm saying is that this plus that, plus meaning superposition, will give you this. Okay, this is superposition. Now, what do I mean by superposibility? Superposibility, very roughly speaking, again, as I said, as that time goes on, my talk is going to become rougher and rougher, vaguer and vaguer. So I'm going to make a very vague statement. Suppose two people, suppose Jyotishman and someone else in the room, say Tuhi, okay, runs two different branching random walks independently of each other. They have, Jyotishman has a picture, okay, snapshot after say million generations. Tuhin also has a picture after million generations, okay. So they'll both get snapshots after a lot of generations. Superposibility means if we superpose these two pictures, the picture of Jyotishman and the picture of Tuhin, we won't see that any qualitative difference in that. This is a very rough statement. Yeah.
So this has to be at the same number of generations.
Yes. Yeah.
And yeah,
A lot of them.
Million plus one won't make too much of a difference.
But million and 2 million may make a difference. Yes, you're right. Yes. Of the same order. Yes. But let's say same number. They like me. Let's make life very simple. Yes. So both of you have a lot of patience. You run this for million generations and you have two different pictures. To superpose them, you won't see any qualitative difference between any of them. All three pictures will be very similar. Well, what I mean by similar is the exact symmetry that it satisfies. There's some kind of symmetry. But it means that if you throw more points coming from another branching random walk, the qualitatively there will be not much. Of course, there will be more points if you superpose them, but at least qualitative picture is not so huge.
Because the question is, if the generations are still the same, the comparison is still the same, but the number of particles will be different, right?
Yeah, that's okay. See, the point is after some stage,
Yes, it does.
it doesn't matter because exactly. So yeah, so after that, actually, I think that's a good question. So that's a good point. Yeah, I think it don't matter. It don't matter. Yeah, but the point is that it may matter. It depends on the scale. If somebody is looking at say million and somebody else is looking at 2 power million, then it may matter. So that's why let's say both million. Okay, so then the see 2 million or 2 million may not matter, but so, yeah. Anyway, so these are all vague statements. But the point is that there is some kind of superposability which can be formalized, which is some kind of symmetry problem, okay, which is satisfied by this limiting point configuration or limiting, picture. Okay, so any question, comment, or concern? Because I've been bigger and bigger.
So this,
Yes. Please, go ahead.
in this slide, that if I say that will the probability distribution be the same in both the cases?
Yes. So probability distribution of so basically what would happen is that the probability distribution of the eventual point configurations, whatever that means, eventual particle configurations, that will satisfy certain symmetry. So that's what I mean.
That's why only superposition.
Yes, it will satisfy certain symmetry, which I don't want to write down because that will take first of all 15 more minutes, and Jyotishman is going to kill me for making it boring for you. So if you want, I can always discuss it. Okay? Thank you for that. Yeah.
So suppose I already for n generation, that is a large number, and I want to make it n times n. So what is the point? How will I access whether the quality will differ on?
Yeah, it's a good point. So it's all vague here, as I said. What I meant by that is that some symmetry is satisfied. That's all I meant. To make it more rigorous, what you have to do is you have to scale. There are some scaling involved. So we have to look at the first picture, scale it appropriately. You have to make it, I don't remember, to make it slightly smaller or bigger or something. So it's going, yeah, you have to make it slightly smaller in a suitable way. The other one also you make slightly smaller, and then you superpose, you won't see stuff. But I'm avoiding all that. So there is some scaling. Yeah. There'll be always scaling involved and the completely avoided. Yes. Okay. Yes.
So I have a question on that. When you were talking of snapshots.
Yes.
Snapshots.
Yes. Right.
Dynamics.
Yes.
So how do you, what reference you take?
Oh, so what I mean is the following. It means like this. So here, so let's anyway. So I showed you how the points run, right? So every time I'm stopping, it's a snapshot. Every generation is a snapshot.
But how do you compute, like, it will be random, right?
Yes, so you'll give a probability distribution on all possible configurations. So that's the answer. But I don't want to get into that. It will involve, point process theory, avoiding all this. It will involve certain mathematics that I will completely hiding under the carpet. There is no carpet here. I assume that there is a carpet, am I hiding under that? Yeah, that will need a lot of theory here. It is not a trivial thing.
I would request now, at least, you can finish, we will take the questions.
Sure, I'll finish. Okay, so I think now it's almost done. So just recall that there were two conjectures of these two famous statistical physicists, Eric Brunel and Bernard Derrida. And then they had this conjecture that it's a limit is a decorated Poisson point process. And it also exhibits what's called superposability property. And then, of course, the first one was answered by Pascal Maya in 2013. That and then there was a question that whether 1 and 2 are the same. Pascal proved under some conditions that they're the same. And the same kind of conditions, Thomas Madul showed that 1 and 2 both hold. He actually showed 2 holds, and then 1 automatically holds thanks to Pascal. Now, key question is what if the conditions are not satisfied? But before knowing that, we should know what kind of conditions Pascal had, or rather Thomas had, same conditions. Roughly speaking, the condition of Pascal and Thomas, the same condition, force the step sizes of most of the newborn particles to be small. Again, you would say, what is small, what is big? Say I tell you that with very high chance, most of the particles are going to take either within plus minus 10 steps. With very high chance. Again, high means what? You have to quantify this. But the chance that will take a very big step is low in some sense. Under that condition, this proof could be done. Now, of course, the ideal question would be, what if we allow bigger step sizes? And what is meant by big also is a question. But what if we allow them? Then, of course, there's a different scenario. And I'm interested in heavy tail distributions. Okay, so these are distributions, probability distributions, which are takes very big value, take very big values. Okay, so then that's where our interest came in, and I gave this problem to Ion and our colleague Rajat, who was actually at that time doing a postdoc in University of Zurich. He came in also. And then the point is, this is the question. DPPP means decorated boson point process, superposibility. Whether they're equivalent or not, Brune and Derrida asked. So if I give you a small number, how can you make it big? Well, I said I'm going to be big, so I'm asking a big question. So if I give you a small number, can you tell me how to make it big? Just give me something. It's okay. You can? Yeah. Multiply by a large number. Very good. But in this case, it so happens that if I just multiply, it may not work. Something better? Exponential. So I just was waiting for that answer. That's sorry, it was a very unfair question, but what you said was correct. Okay, it's a good base. So one of the ways to do it, in this case, it so happens that exponentiation is the right thing to do. Like if it's 10, you make it 2 power 10, it becomes 1024, the bigger number. Okay, so by exponentiating all the particle step sizes, superposibility will change to what is already known as stability. Don't tell me what that is. Some kind of symmetry. That's already known. Similar exponentiation, if I do at the level of these decorated Poisson point processes, they become what is now known as, okay, this name wasn't given, we coined this term, scale decorated Poisson point processes. So the point is some shift will become scale. So if you exponentiate, whatever is sum will become product, right? X plus y will go to e power x plus y, which is e power x times e power y. So therefore, anything that's a shift will become a scale. Okay, so exponentiation will make this change. And then the interesting part is these two are known to be equivalent because of Derrida, Molchanov, and Zuev. Their paper in 2008, we already proved it, and there is an improvement in 2011. So stability and scale decorated Poisson point process, which are obtained from superposibility and decorated point process respectively, by taking exponential, which is supposed to make the step size bigger, are already equivalent. So if you exponentiate, how can you go back? What is the opposite? What is the inverse operation? Log, right? You have e power x, you can take log, right? So take log. If you take log, you just go back in both directions. And this is actually a proof that the question asked by Brune and Derrida has a positive answer. However, I'll get back to it, maybe in the end. So, however, this was not the proof that Pascal Mayer gave. He had a different proof. He used a direct, I call it direct frontal attack kind of proof. Okay. Okay, so but this is a picture. So essentially this means, but this picture, what's the point of this picture? The point is that if we want to prove Brune and Derrida conjectures in our setup, where I'm expecting the step sizes to be big, superposibility is not the right symmetry. I should look for stability. The limit should not be a decorated Poisson point process. It should be a scale decorated Poisson point process. So the statement of the conjecture has to, has to adapt to the new situation. You have to change the meaning of Brune-Derrida conjecture. That is the right meaning. In many cases, understanding the right meaning takes a while, and once you understand it, proof is just a matter of time. So that's what happened here. Once we understood it. So this is the upshot of what I just said. So you should replace DPPP by SCDPPP, scale decorated Poisson point process, and whatever is superposibility should be replaced by stability. And then we could prove in our papers. The first one is the one I'm referring to. Second one has a little bit more complicated setup, but let's just consider the first one. We could prove that under this change, under this adaptation of replacing superposibility by stability and DPPP, had I said enough? SCDPP, replacing DPPP by SCDPP, you can actually prove these conjectures. Okay, and it's enough to prove one of them, right? Because the other one will follow thanks to Derrida, Molchanov, and so on. Not only that, we could actually explicitly compute that long-run configuration in our case. It so happens that when things are heavy-tailed, calculations sometimes become a bit easier. Okay, today I was discussing with you, it's because of one large chunk. Anyway, so this is missing, this explicit description is actually missing in Thomas Madhul's paper. So this is missing in the small step size case because there, Thomas Madhul just proved that the limit exists. Well, there is a long run configuration and it satisfies this superposability symmetry. And hence it is repeated. So his proof is existential. We could actually tell you exactly how it looks, which has a lot of advantage. I'll tell you that. So before going there, so for example, I can now tell you, say if you look at this whole system, one of the questions that you can ask, forget all the things. Where is the rightmost particle after nth generation? I can tell you that if it's a branching, binary branching, and Mohan is in the room, so we can assume that it's a binary branching. In the binary branching, I can tell you that the rightmost particle will scale like something, 2 power some n over alpha. The alpha is a parameter coming from the distribution. It don't depend on the explicit distribution, but some parameter of the distribution. That's all. And after scaling, the rightmost point will converge to some known distribution. That's it. So anyway, let's not get into all the mathematics, but this is the summary of everything. So I'm coming back to my collaborators. Oyon is now in IIT Bombay, who is an assistant professor there. And Rajat, we have unfortunately lost him from the Indian academia, which I think is a huge loss. He's a very, very, very good mathematician. So he's an assistant professor in Leiden University. And I want to acknowledge a few people, apart from you guys, of course, for listening to me patiently. My friend Mohitosh Kejriwal, who is actually an econometrician, he actually he found some typos in the first version of these slides. I told you that this, I told you, right? I've given out this talk only online. During lockdown, I gave this talk first to some students. And then now I'm first time giving it both in person as well as online. So it's more challenging. I think hybrid talks are more challenging. By the way, was there any question from the chat? No. Okay, not yet. Okay. And then also my school friend Sudipto Das, who's also an academician, he works as a statistician. He actually suggested how to explain superposition using pictures. And as you know, a picture is what 1,000 words. I could have said 1,000 words. Instead of that, I just drew that picture and then superposition became clear to all of them. So I think I acknowledge them. And then, of course, that's the end of it. So thank you very much. So I went to page 67. So yeah. Anyway, go ahead.
Okay, yeah, questions.
Yeah, I think partly answer about the
Sure.
whether it depends on the whoever distribution or not.
Well, it depends to some extent.
Yeah,
Some parameters.
yes.
Yeah.
If you take a probability distribution not uniform, but there's a scale in the probability distribution itself,
Right.
then you cannot just exponentiate.
Right. Yeah, so it does depend on the distribution. Say, for example, if you initially had exponential distribution and you exponential, then I know how to answer this question. So, say, for example, in the heavy tail case, which means there are a lot of big values, the whole system, see the binary case, again, Mohan is away, so binary case. As I said, the whole system actually grows, or the rightmost point and the leftmost point, both their position, if you look at it, they grow up the scale of 2 power n over alpha, where alpha is some parameter that comes from the step size distribution. So there is one parameter of the distribution that plays a role, but not the entire distribution. So you don't have to know the exact distribution, you just have to know this parameter. So this parameter is called tail parameter of the distribution. So if you want, I can be a little more mathematically precise later offline. Okay. Any other question? Yes.
And may have missed this, but if you say that we are not going to explain, but as a DPP.
Yeah, it's very hard. So do you know what is a Poisson point process? Okay. So there is something called Poisson point process, whatever that is. It's a system of points thrown on a line. Okay. What you have is you have many such Poisson point processes, infinitely many actually, and then you have their mixtures. In some mixtures, you mix them in some way. Okay, so it's a complete set.
What is the Poisson point process? If there is a very simple definition exists, what is the Poisson process?
Yeah, it's hard to explain.
Okay.
Yeah, I'll try to explain you a little bit. So it's something like this. You would count the number of points. So you have a line, right? So I think here, if I write, yes, this will be. You have a line. So you look at this point. So you have many points. You have point configuration, right? You see line like this, an interval like this, and count how many points are there. That's going to be always finite with probability 1. Okay. And whether it only depends on the number of particles, the distribution of course the particles are in the random position. So number of particles is a random variable. Its distribution will only depend on the size, on the length of this interval. You can have the interval here also. Say if it's the same length, the number of particles will follow the same distribution. Also, if you have two disjoint intervals, the number of particles here is a random variable which will be independent of the number of particles here. That is quite natural. And all of these distributions will be what is called the Poisson distribution. That I'm not explaining, but there's some distribution. So roughly that's what this means. Now you have many such Poisson processes, Poisson point processes, and you have their mixtures. So the mixture is happening in a decorated fashion. There is a decoration, a distribution, decoration distribution. So that's why it's called decorated. So yeah, so that's all I would say.
Yeah, thanks.
Yeah,
There
sure.
could be something to understand.
Sure. Thank you. Yes.
A naive question.
Yes.
So when you talk about after dynamics, large time
Right.
symmetries appear. So the scale is easy to see.
Right.
Are there any other symmetries in your mind?
Good question. It may depend on the distribution. For example, if distribution already has some symmetry, it will be preserved. For example, if it may not be killed, I will just say. So the distribution is already symmetric. You do binary simple branching number.
That's not interesting.
That's not interesting, but I'm just giving you an example. Then of course this will have the symmetry. There's a leftmost point and the rightmost point will scale, will not only scale similarly. If you look at how far they are, the distribution will also have the same kind of scaling limit. So if you have any kind of symmetry in the distribution, it's expected that that will be preserved, but not necessarily all. What are preserved are the questions. So those are actually good questions. So for example, if we assume that the first distribution has certain probabilistic property, will it imply a similar probabilistic property of the limit? These are all good questions.
No, what I mean is, can you get symmetry that emerges because of the large?
Oh, that's, okay. Okay. I understand. Now I understand. I think in the heavy tail case, I can answer you that this decoration, for example, it's not really the symmetry, but this decoration is not there. Decoration meaning that it's mixture of many point processes. Decoration, this is emerging because of the large scale limit, which was initially not there at all. That it would be Poissonian is sort of expected. Again, I'm hiding a lot of things, but the fact that there is a decoration, it's coming in because of the limit.
So
And this can be made precise. This stuff. Yeah.
I have a quick question.
Actually, they both have questions. Dulan has another one and we
Yeah.
Sure.
And this quick question, most of the time when we're looking for sort of explanation to a population, a distribution that we see for a bacteria, for example, after a long time, like we have reached some equilibrium, right? There has to be some symmetry that we can infer from say taking snapshots, so that we can come back to your model. I'm just trying to see
That's
where I
very
can
good.
apply this, right? If it was just
Yeah, that's a very good question. So essentially what you're asking
so then
is say you have data.
right, I mean,
Will you be able to test statistically whether it comes from this model?
this model,
That's a very difficult question. We have actually tried some estimation. Testing is the next step. First we try it. Even that was very hard. But I think these are all very good questions that we are thinking of solving eventually. So hopefully at some point. Yeah, thank you. That's a good question. Yes.
So, if you have in this scenario, if you have some probability distribution of the step sizes, is the effective probability distribution of the particles, are you basically convolving the probability distributions multiple times?
You are convolving, except that there is a very strong dependence which you have to handle. You are convolving because you are adding independent random variables.
Right.
But it's a very complicated. If you look at the joint distribution, each of them marginally is a convolution. Marginally meaning if you just look at one particle after million generation, it's a convolution of million sums. So it's a convolution of million. That's complicated, but that still can be handled. The problem is that there are so many of them, say binaries, and 2 power million of them, and there is very strong dependence. Nor is there in stationarity, so it makes very complicated. Yeah, that is the
So
complication.
basically, yeah, so doing it that way would not be a mathematically feasible.
It's very difficult, yeah, but you have to somehow keep track of who's coming from which particle, which two particles have the same ancestor, etc. That has to be done.
We need to do that, like all particles are technically identical, right?
You have to do it to some extent, in the sense that, well, so you have to say for example, forget everything else. I'll come back to it. So suppose you're only interested in what happens to the rightmost particle. Basically, you're looking at the maximum of the positions in the energy generation. Now, this rightmost particle, why does this particle go so far? In the heavy tail case, like in our case, our setup, it can be shown formally that this is happening because either that particle itself or one of its ancestors took a big leap. It's called one large jump principle. And that big leap, where that big leap can be, it's of course a random variable. Finding out that distribution of that random variable becomes important. So that's the rough idea in the heavy tail case. In the small tail case, it's very difficult because there are contributions from small contributions. So we have to be, it's more complicated. That's why they don't have the explicit.
That doesn't interest you.
Yes.
Yeah, so I'm intrigued with this number of alpha.
Oh, I can tell you. It's a power law.
I can imagine that. So the range of alpha is all the way from 0 to 3.
Yes, it's a power law distribution.
Yeah, it's a power distribution. The thing is that, so if it is very, very heavy tail, then I presume that alpha will be very small.
Yes, yes, closer to 0. Closer to 0. Yes.
But I can imagine many shapes of stuff. It's not just it doesn't have to be just heavy tailed in the extreme sense that there is only, plus 100 and minus 200 of the steps. There are many things like that.
Yes.
So, but there's still one number. What is this other? How do you get it from?
Oh, okay, I can tell you what it is. Yeah, I can tell you. So now I can be a bit more notationally heavy, I guess. So suppose your state size, this random variable is S, so S stands for state. So what you would do is your probability that S takes a very big value compared to, say, U. So it's bigger than U. For big U, when U is large, okay, when U is close to infinity, this will be the close to some constant times 1 over U power alpha. But alpha is a number, alpha is a parameter. Alpha is strictly positive and sub is finite. It's a number. So I say alpha is 10, it doesn't matter, you can fix it. And then it's like this. So that's the power law table. So the tail of its state size is a power law. Then this parameter alpha, this 10, this will mean that the maximum or entire system is actually going to grow like, say it's a binary, 2 power n over 10. So the nth generation, if you look at the entire system or look at just the rightmost point, position of that, it will scale like this. So yeah, so in general, there will be an alpha, which will appear here. The alpha is some positive number, finite, then you will see this here. And then this 2 is coming from binary. If it's trinary, it will be 3. If it's tertiary, it will be 4.
Yeah. I think we'll stop here for some snacks and we will ask the question during the
Sure.
That would be great. Very thanks for all the questions. Yeah. Thank you very much, Parthanil, for a fantastic talk.
I was very nervous.
You were going through everything with particular definition, stress to every point. That was very, very
Thank you. It's an honor.
nice. Thank you.
I'll join there.
Yeah, please. All of you are welcome to the snacks. There's samosa.
I'll definitely love it. Yes. Okay. Become, whatever shift, yeah, exactly. Shift is going to.
Okay.
Next to meet you.
Yeah, so we can have okay, so I'm using the room on the 3rd floor
of E block. Okay, math office, next to that. It's between math
So
office.
we are going to end the session here, so thank you all for joining.
For any question online, can you please check? Anybody wants to
Happy to make.
Sure, please, let's go on. Let's go on.
Thank you very much. For those in the audience in TIFR, you can come and join and have some tea.
Oh, some of them might actually, I heard them online. So,
Right. Okay.
So there was no question, right? Everyone should have asked, in case somebody wants to ask something, we should have.
We have the video on.
Okay,
So we will discuss it.
okay,